Today we're talking about Chapter 3, Section 4, Transformations of Functions. So in 3.3 we went over a whole host of functions and I told you that you need to memorize them. Okay, and the reason why is because of this section. We need to be able to know how to transform these functions. Okay, so we need to have the review of these functions. Right, I'm not going to waste any time on those today though. That should have been something that you would have done. Okay. Alright, this says, and we're just going to snip the example here because this is kind of showing you the old way of graphing functions. We'll go ahead and put it on the current page. Okay, I said this is the old way of graphing functions because I mean this is sixth grade stuff, right? You're given a function, right? And well, it's actually yes. Well, it does say sketch the graphs of the absolute value and then the absolute value plus 2. Okay, and so sketching the absolute value, if we plug in a -3 for x, then we get a +3 for our output. If we plug in a -2, we get a +2, and so on and so forth, because it is the absolute value function, right? The absolute value of any number, positive or negative, is that number. Likewise, if we were to take that same absolute value and add 2 to it, right, then we would have, we plug in -3, well, the absolute value of -3 is 3, and then if we add 2 to it, we get 5, right? And then we can see the same thing with, like -1. The absolute value of -1 is 1, and if we add 2 to it, it's 3. Okay, notice how every time that we add that 2 to it, we are going up, those 2 units, right? We're going up 2 units on the y-axis. Okay, so this would be an example of a vertical shift. And let's see if they give us a handy-dandy graph. Yeah, they do. Okay, good. Oops, cut that 2 off, didn't I? Okay, in the red you see the absolute value function, and we've seen that as a parent function, right? But in the blue, notice how we take this red line and we move up 2 units pretty much everywhere, right? Right? Again, that is an example of a vertical shift. This table that we see here, all right, we're no longer going to be doing it. Okay, we are beyond tables. Again, tables is 6th grade stuff. Tables is your little brother, sister, cousin's homework, not yours. Instead, what we're going to do is we're going to look at functions. We're going to be able to say within 3 seconds exactly what we do to that graph, the transformations of that graph. Okay, the first thing we're going to talk about is vertical shifts. Okay, let me see if I can't put something else on there. Not necessarily. Okay, so we'll go back. We have room for. Okay, yeah, we kind of do. Sorry, so let me get my bearing straight here. Let's erase this, or maybe we can put it on another. No, we'll just erase it. So we'll move this up, all right, and then this is the star of the show. So I'm going to put a big old arrow to it and a star. Okay, that is the star of the show here. All right, so vertical shifts of functions. If c is a positive real number, the graph of y is equal to f of x plus c is obtained by shifting the graph of the graph of y is equal to f of x vertically upwards c units. Right, and then the opposite is true going down, right? the graph of y is equal to f of x minus c is obtained by shifting the graph of y is equal to f of x vertically down c units. Okay, so what does this mean? Well, if we have, and this is basically just saying this right here, let's make it go back thinner. This y is equal to f of x plus c. Okay, well, it's saying that some y, the y value of our function, right, is gotten, whatever, is gotten by taking the parent function, all right, the parent function, whatever it may be, the parent function, right, and then plus c means we're shifting up c units, and we can see an example of that in example 1, right? We have the parent function being the absolute value of x, and then we're shifting it up 2 units. Okay, now if this were a minus 2, then we would take that graph and we'd shift it down to, and that is actually really good. Okay, so we're going to keep that. We're going to keep that. If we had absolute value of x minus 2, all right, that is this graph. Yeah, perfect. Okay, that is vertical shifts. Super duper easy. Okay, probably the easiest. Well, I mean, of course, we start off with the easiest thing in the section, don't we? Probably the easiest transformation in this section. Okay. Next up would be a horizontal shift, and we'll talk about that right here. Let's see if we have the. We can do the star of the show thing again. Yeah, we can. Okay, good, good, good. Okay, let's snip this. I don't really care about that graph, mainly because I'm pretty sure in order to see the transformation, we'd have to click on that the illustrate button, which you are more than welcome to do when you look at the textbook yourself. Okay, so we're not gonna bother with that right now. Okay, so here we go. So similar to our absolute value equation that we had for the first example, and how we did a vertical shift up 2 units, and I also showed you what a vertical shift down 2 units looks like, we also have a horizontal shift. Okay, so again, we're doing our tables here. Excuse me, we're doing our tables here, and again, the tables again they are going away. This is just kind of showing what happens if we do it, our old way, but we do know that the absolute value, or I'm sorry, when f of x equal to x squared, we do know it is this red graph there, right? Because you, like a good student, memorized what these parent functions were. So real quick, how many do we have? We have 9. We have 7 students today. Okay, so you 7, all right, you 7 are very serious about this. So you definitely paid attention Tuesday and memorized Tuesday, right? So knowing that, we do know that the x squared function looks like this parabola. Okay, well, if we were to add 2 to the variable, okay, now it's very important to distinguish the difference between adding to the function and adding to the variable. Okay, and I'm pretty sure the next example that we do really highlights adding to the function and adding to the variable. Okay, but if we're adding 2 to the variable, then we're going to move left. Okay, so let's actually write that down. Okay, so if we if we add, we'll put variable v. If we add to the variable, then we move left. If we subtract from the variable, I was going to try and spell it, then we move right. Okay. Oh, but that doesn't make sense. Okay, well, that's because you're not thinking straight. Okay, here's why. Let's take a look at this function here. Okay, if we were to take, I guess we can erase this arrow. If we were to take this function, g of x is equal to x plus 2 quantity squared. Okay, and I said find the zeros of this function, right? Where does this function touch across the x-axis? What would you do? Well, you would take this and you would equate it to 0. X plus 2 is equal to 0, and therefore we have an x-intercept at x is equal to -2. And of course we can see that in this graph right there. Okay, so that's why if you add to the variable, you move left, and if you subtract to the variable, you move right. Okay, admittedly it is seemingly counterintuitive, especially when the vertical shift is so pretty plain, right? Add to the parent function, we go up. Subtract from the parent function, you go down. Well, horizontal does make sense, but it is, I would say, counterintuitive. Okay. And honestly, that pretty much summed up what this says. Okay, so what is the difference between adding to the variable and adding to the parent function? Okay, this would be a perfect example of adding to the variable and adding to the parent function. Okay, so this says, use the graph of y is equal to x cubed to sketch the graph of g of x is equal to x minus 1 quantity cubed plus 2. Okay, so let's write that nice and big real quick. G of x is equal to x minus 1 quantity cubed plus 2. Okay, so looking right away here, I can tell that the parent function, okay, so the parent function, we're just going to denote as PF, the parent function is x cubed. Okay, so that's the first thing that we're going to kind of graph is the parent function. So let's do that. Not what I wanted. No. Okay, I'm going to put it over here to the left because I'm going to put the actual good graph from the textbook on the right. Alright, that's good enough. Alright, so this tells me that my parent function is x cubed. So let's, I guess, yeah, I've got enough colors. Okay, so in the blue, we got to recall that my x cubed looks something like, well, let's actually make it thin so it's not the finished product. Looks something like that, right? That's what x cubed looks like. Okay, well, next we're going to look at this negative 1 here. Okay, and this tells me the horizontal shifts. Let's move this to the left. Okay, so this tells me my horizontal. Let's go back to medium. Sorry about that. Lots of stuff. I gotta have a nice finished product, right? This tells me my horizontal shift. Okay, so we're gonna take my blue graph down here and we're going to shift it left 1 unit. Okay, well, now here's what you do on every one of these parent functions. Okay, now we will see later on when we get to exponential and logarithmic functions that what I'm going to call the landmark. Okay, the landmark changes. Now the landmark is basically the point that you're going to move around. So imagine if you have if you can take the point, I'm right here on the graph. Maybe I should have made it red, huh? Okay, so looking at the graph over to the right, if we were to take that point right here and we're able to move it, you know, up, down, left, right. Okay, that is what we're moving. Okay, and I call that the landmark. Okay, every single one of these parent functions have that landmark at the origin at 0, 0. Okay, so what I'm going to do here is I'm going to take this function, or this graph right here, the parent function, and since it is a minus 1, I'm going to move it to the right 1 unit. Okay, so I'm going to take the landmark, okay, the landmark being right here at 0, 0, landmark on my parent function, I'm just going to go right just 1 unit. Okay, so we're going to move it over 1 unit, so now it looks something like this. Okay, so that would be the horizontal. Did I say stretch? I got ahead of myself. Sorry. No, I'm sorry. Yeah, I did horizontal shift. The horizontal shift, we move it to the right 1 unit. Okay, and then lastly, okay, we see this plus 2 here. see this plus 2. Oh, that is an eraser. Plus 2. And this is going to be the vertical shift. Okay, so again, the question arose, how do I know the difference between horizontal shift and vertical shift? Okay, horizontal shift will be added or subtracted from the variable. Okay, in this particular case, an x. All right, most cases, right, we do x's, but obviously we've seen y's and z's and a, b's, and c's, right? But the vertical shift is going to be added or subtracted from the entire parent function. Okay, so this is a vertical shift up 2 units. So again, our landmark, right here, the one that we moved to the right 1 unit. Now we're going to move it up 2 units. Okay, so moving it up 2 units, it's going to look something like, and I guess we can just make this nice and big. So something along the lines of that. Okay, and of course the graph that I'm going to give you is a lot more precise. And of course you will have let's see, you'll have graphing utilities in your homework to do this better. But anyways, to recap, right? The first thing we did was we identified parent function. Okay. The second thing we did was the horizontal shift, and the third thing we did is the vertical shift. Okay. Now, why did I put the horizontal shift before the vertical shift? The reason why is because there is a procedure involved in doing transformations. Okay. The first thing we always do, right, besides identifying, right? The first thing we always do is horizontal shift. Okay. And then the last is always going to be vertical shift. Okay. So this is always going to be first, and that is always going to be last. Vertical shift is always going to be last. Okay. So now we got. Okay, so it doesn't give us a nice, pretty graph. So we're just got to take my word for it. Okay. Now we're going to get to something a little bit tougher. We're going to be talking about reflections. Okay, it's not that hard though. So reflections of functions about the x-axis. So if we have the negative of the parent function, okay, then what we're going to do is we're going to reflect that parent function over the x-axis. So let's see if we no, okay, so we'll snip both of these, I guess. Crazy we don't have an example there.
Mr. Brown?
Yes.
I believe there was an example, but it was on the slide before that, before the animation. Before, one more time. Is that the example you were looking for?
Not necessarily, because this is using a calculator, but it does. Let me see what other examples there are, because I know we're going to come across some, hopefully. Yeah. So we do have examples regarding that. And actually, let's go ahead and snip that. Yeah, I don't want to work too much on calculators, although it did have the reflections, like you did say, but I don't want to do it with a calculator.
Okay, sorry about that. I didn't know.
No big deal. All right, so here we go. Okay, so how can I maybe like this? Okay. So again, reflection about the x-axis. What we're going to do is we're going to take the negative of the parent function, and then if we take the negative of the parent function, then we did I get a chat? I think I got a chat pop up. Again, if you need to message me, message the sample student, or just chat it to everybody. Anyways, okay, yeah, a third time. All right, so we take, if we have the negative of the parent function, then we're going to reflect it about the x-axis, and we're going to see an example of that here. Okay, and if we take the negative of the variable, Okay, then we're going to reflect it about the y-axis. Right, so let's go ahead and graph those and show you what they look like. I guess we'll make two separate ones. I'm pretty sure I saw an actual graph this time. So again, we might have prettier prettier graphs this time. All right, so A. So what is my parent function in A? Okay, so my parent function in A, again, is going to be my, well, actually, not again, sorry, is going to be my cube root, okay? So my cube root, if you recall, looks like an S, like that, okay? Excuse me. All right, but it is reflecting about the x-axis, right? Because notice how it is the negative of that parent function. Okay, so what we're going to have to do now is we're going to have to reflect this white line that I just drew, my cube root function. I'm going to have to reflect it. I'm going to basically rotate it around the x-axis. So rotating it around the x-axis will look like this. Okay, and then lastly, we see that we have a vertical shift down 2 units. So we're gonna take a look at this landmark again right here at this 0, 0, the origin, and we're gonna shift it down 2 units. Okay, and again we're just kind of eyeballing this, so we're gonna shift it down to about right here. Okay, and so the green is my actual function. Okay, and again that is that's very poor actually. Let's try that again. Should be more like, whatever. Y'all get the point. And that's it. So we look at our parent function, okay, and notice again how I did my reflection about the x-axis, and then I did my vertical shift last. Okay, so that is going to be a common theme because my vertical shift is always going to be last. Excuse me. All right, and then next, B. All right, so again, the parent function is the cube root, so it's going to look like this. Okay. All right. Well, this particular graph, all right, is 1 minus x. Okay. So what are we actually doing to this? So let's actually look at this. Oh, I changed color. Let's actually look at this and put it in terms of the x in front. Okay, only because I feel like it makes it a lot easier to look at. Okay, so let's do that. So we've got cube root, and then we're going to have a negative x plus 1. Okay, so the reason why I did that is because notice how now we can see I mean, we could have probably seen by just not changing anything, but now it's abundantly clear that we are adding 1 to the variable, okay, and we are flipping it across the y-axis, okay, because we're taking the negative of the variable. Again, in A, we take the negative of the function, then we flip it across the x-axis. In B, we're taking a negative variable, and we're going to flip it across the y-axis, okay? But again, remember how earlier I said first is always a horizontal shift, okay? So we're going to make a horizontal shift to the left 1 unit first, right? Because since it's a plus 1, we're going to shift it to the left 1 unit. So we're going to go left 1 unit. Sorry, I'm trying to make it thin here. Left 1 unit. So it's going to look something like this, okay? And then we're going to do our excuse me, our vertical reflection across the y-axis, okay? So this, oh gosh, it's going to look a little ridiculous. Sorry, but it's going to look something like, we're just going to reflect it across the y-axis, okay? So again, all I did was try to reflect that blue line with that green line, okay? And that is the reflections. So let's actually now get, well, there's 3 of them, so let's see. Alright, I'll put it on another page. How about that? I'll give you the good graphs on another page. Okay. Okay, now we get to the last part of our transformations, and that will be vertical stretches, compressions, and horizontal stretches and compressions. So, like we have done so far, we're going to do again. We're going to do this table just to really show what we're looking at here. Okay, so use the graph of f of x is equal to x squared to sketch the graph of g of x equal to 2x squared. Okay, so if we were to, and again we see over here, then we know x squared is a parabola, right? So it's a parabola, right? And we just start with we're starting here at -2. So we plug in if we plug in a -2, well, -2 quantity squared is 4, okay? And then if I take that 4 and then I multiply it by 2, right there, right? Again, it's 2 times the x squared. We take that 4 multiplied by 2, we get 8, okay? We plug in a -1, -1 squared is 1, and we multiply that 1 by 2, we get a 2. Okay, so notice how, and we know, again, we know the behavior of the parabola, the red line, but the blue line, notice when we are multiplying the parent function by a number, by a whole number, it appears that we are kind of stretching that blue line, aren't we? Okay, we're kind of pulling it. All right, this is an example of a vertical stretch. Okay. And next will be a vertical compression. Okay, so same thing. Notice how we know the behavior of our red line, our quadratic, right? X squared. All right. Well, if we take -2, we multiplied it by +4. Okay, same thing. It's always a 4, right? Because that's a quadratic equation. But then we're going to multiply it by some fraction. Okay. In this particular case, we're going to multiply it by 1/2. Okay. Well, half of 4 is 2. Okay. Half of 4 is 2. Same thing can be said, if we have -1, well, -1 squared is 1. If we take half of 1, that's half. Okay, so what we're seeing here is an example of vertical compression. So notice how, again, the red line is my parent function, but my blue line, imagine that we have this graph in a hydraulic press, right? We have it in a hydraulic press, and then we are slowly squishing it. Okay, we are taking that red line, and then by squishing it, the blue line is kind of getting flattened out, right? There's a vertical compression. Okay, and then again, to recap, normally when I'm in my class, I kind of do I clap my hands, for a compression, well, horizontal, I guess, but vertical stretches and stuff, just kind of pull like I got nothing, right? Like we just kind of we take the graph and we just kind of pull it apart. Okay, that would be the vertical stretch. Again, the vertical compression would just be if we just flatten it. Okay, and this is our summary. Okay, so what exactly makes it stretch and what makes it compress? And again, this, is going to be the star of our show down here. Vertical stretches and compressions of functions. Suppose a is a positive real number. Okay, so notice how a is the number in front. Maybe I should put it in red. I don't know. I feel like red is more commanding. Notice how Notice how a is in front of my parent function. Okay, so suppose a is a positive real number. The graph of y is equal to a, all right, some number times my parent function, is obtained by multiplying each y coordinate of y is equal to f of x by a. Okay, that's obvious, right? We in this particular case, my a is 1/2. We multiplied my parent function, or what I received from my parent function, by 1/2. And on the previous page, we multiplied it by 2. Okay. Now here is the big time stickler. Okay. If a is greater than 1, okay, so if a is greater than 1, we will obtain a vertical stretch. Okay. If a is between 0 and 1, and notice how it is a strictly greater than here. Okay, if a is strictly greater than 1, all right, then we stretch it. If a is between 0 and 1, okay, again, strictly between 0 and 1, not 0 and not 1, but between 0 and 1, then we're going to compress it, okay? So a good way just to think about this is if a is well, if it's a number greater than 1, that's pretty obvious, right? But if we say it is between 0 and 1, well, it's basically just going to be any fraction, right? Any fraction that is less than 1, right? 3/49, right? That's not whole, yeah. 3/49, right? That's a fraction. Any fraction in front of my parent function tells me I'm going to compress it. Okay, well then you might be asking, okay, well this is for strictly greater than 1, and this is for strictly between 0 and 1. Well, what happens at 1, and what happens at less than 0? Okay, well what happens at 1 is, well, it's just a parent function, right? 1 times a parent function is a parent function, so that takes care of this, right? Well, what happens when it's less than 0? Okay, well the less than 0 we've already talked about, because that would be the negative of the parent function, right? So what we're really just looking at, strictly looking at, is just that number. We don't give a crap about its signs, nothing, just the number. Okay, if it's negative, again, if it's a negative 3x squared, okay, well that would be a vertical stretch, right, because it is a number greater than 1, and then it would be flipped across the x-axis because it is the negative of the parent function. Okay, so that is taken care of. Okay, and horizontal. I think we can just yeah, we can just pull this. Okay, so similar to how the vertical shift, right? Vertical shift was very intuitive, right? If we add to the parent function, we go up. If we subtract from the parent function, we go down. All right. But the horizontal shift was kind of not intuitive, but it does make sense when you solve for 0, right? So like if we added x plus 2, what does it say, cubed, right? If we added 2 to the variable, then we shifted left 2 units, right? So it wasn't intuitive, but it made sense because we know that when we solve this for 0, we get x is equal to -2, which would be the 0, right? Well, horizontal stretches and compressions, I wouldn't say operate the same way, but if you memorize that horizontal and vertical shifts, they're pretty much opposite. Well, then horizontal stretches and compressions and vertical stretches and compressions are kind of opposite, right? So, for instance, again, let a be a positive number, okay? And similar to horizontal shifts, how we add or subtract from the variable, horizontal shifts are if we multiply the variable, okay? Again, vertical stretches and compressions are if we multiply by the parent function. Horizontal is if we multiply by the variable. Again, it's kind of the same relationship that the vertical and horizontal shifts have, right? Vertical is to the parent function, horizontal is to the variable. Same thing with vertical and horizontal stretches. Okay, well, this is where the opposite comes in. So if a is greater than 0, remember in vertical shifts we stretched it. Okay, well, if a is greater than 0 and we're multiplying, greater than 1, and we're multiplying the variable by that number, then we are going to compress it. Again, just the opposite. Okay, and if a is between 0 and 1, right? Then we will be stretching it. Okay, and again, compression. You know, imagine you're clapping your hands, right? You clap your hands, you have your compression. Okay, and then horizontal stretch. You just kind of imagine that you're playing an accordion, right? You're stretching it, and that's the behavior of horizontal stretches and compressions. So again, let's see. We've got okay. This one actually does have a compression graph. It doesn't have a stretching one though, does it? Oh, okay, it does. Never mind. Okay, so I'll still do it myself, but then I'll snip both of those. Okay, so just make it a little small because I really want to fit those onto the page. All right. So starting off with 4x. Okay. So since we are taking the we're taking the variable. Okay, we're multiplying the variable by a number that's greater than 1. Okay. Well, first of all, I got ahead of myself. Let's sketch our parent function. Okay. So parent function is the square root function. So again, that function looks something like I was doing blue. Looks something like that, right? I don't know if y'all can see that. I think I made this graph a little small, but that's fine. Again, I will snip the better graphs. All right, so my square root function looks like this. Okay. Well, I'm multiplying it by 4x. Okay. So multiplying it by 4x, that is a number that is greater than 1. Okay. So remember, in vertical shifts, that number greater than 1 is a stretch. Okay. Well, for horizontal, it's going to be compression. Okay, so we're going to take this blue line and we're just going to kind of squish it like an accordion, right? And so it's going to look something similar to this. Okay, yeah, that's horrible. That's fine. That's fine. That's going to look something similar to that. Okay, and then likewise, let's say this will be g of x. Green is g of x. Okay, again, g of x being right here. And then we'll let yellow be h of x, so I don't have to draw too many graphs. All right, so what we're going to do here is it is a fraction, okay, and the fractions, all right, is going to be a horizontal stretch. So we're going to take this blue line and we're going to stretch it horizontally, okay? So it's going to look something along the lines of this, and that's going to be h of x. Excuse me, okay? And so let's go ahead and get the nice, prettier graphs going. Okay, so there they are. Yeah, that's good. Okay, so we went over a lot of stuff, and I told you that there is a way to do it. Okay, there is a certain procedure rather to go about this. Right. Well, here's the thing. You can, all right, you can memorize all of these if you want to. Okay, and if you do, all right, something that I would suggest is a mnemonic device. Right. We have an H H R V R V. I mean, you could think of something. I've again normally in a class I'm like, hey guys, so let's come up with one. But with the exception of somebody that spoke earlier, I try not to get you guys to speak because these do go on YouTube, and there are FERPA laws in place, right? So with that said, come up with one by yourself, a mnemonic device. If you don't know what a mnemonic device is, we can say like, I don't know, Harry has real vinyl RV. Hey, that's pretty good. I haven't even thought of that one, right? So like Harry has real vinyl RVs, HHRVRV, right? Now we need to be able to distinguish it between the two RVRVs, but you get my point. Now here's the thing: if you don't feel like doing that, which is one of the rare cases where I think it is okay, then all you have got to remember is that first is always horizontal shift. If that is available to you, always do that first. All right. And last is always vertical shift. Right? And if that is available to you, always do it last. Realistically, if you memorize those two, at least for this class, I mean, I'm just gonna say with 99% certainty, you'll get everything right. I say 99% because there might have been a problem I haven't seen where that didn't work. Okay, so if you did it that way, and you might have been the 1%. But for the most part, like I said, everything I've seen in this course, um, and honestly, even for pre-calculus algebra, horizontal shifts is always first, vertical shifts is always last. This stuff in here, bleh. Okay, so hopefully that helps you out.
Mr. Brown,
Yes,
I just realized there may be another way to remember that as well.
yes.
About the first and the last part.
Mm-hmm.
Wouldn't it work the same way if you just simply work the equation from left to right? Because the vertical shifts are always on the right side of the equation, are always on the very edge of the equation.
Yeah, you are correct. You are correct about that. But I will say mainly because it's so tempting to, and let's see, I'll give you an example. It was like it was this example here actually. I just feel like it's kind of tempting to go ahead and do that vertical shift because it's just there. But yeah, I mean you are correct. You do read graphs left to right, but there's that.
Okay, I was just curious because I remember that's how I remember the
Hmm.
difference between shifts is that I always work the equation from left to right when I'm dealing with transformations.
Yeah. Well, I mean you a lot of times, I mean, what I say, other people come up with ideas that are just better for them, and then that goes for everybody, I guess. If you have a better way to think about it, better way to memorize, then go for it. Okay.
Okay.
All right. So last up, well, I won't say last up actually. We're going to now combine all of our shifting here. Okay. So use transformation to sketch the graph. So here we go. Let's. This does have an actual graph. Okay, good. So we can kind of go crazy over here to the left. Okay, so let's do. Okay, we've got one. Two, we just have three transformations here. So we're going to denote them in their colors. Okay. So the first thing I'm going to do is I'm going to draw my parent function. This is a parabola. I always never take it off the line, do I? All right. So it's going to be a parabola. Looks something like this. It's a little round, but that's fine. Okay. All right. So we're going to do the first the first transformation we're going to do, okay, is the one that I said we always do first, right? It's going to be the horizontal shift. So we're going to, it looks like, so it's a +3. So what we're going to do is we're going to go left 3 units, okay? The second transformation we're going to do, okay, looks like it's going, it's kind of, I guess it is kind of 4, so that's fine. So the second transformation we're going to do is we are going to flip it across the x-axis. So it's going to be a horizontal. I mean, I hesitate to write hor. Well, maybe we'll write hora. Horizontal. We'll put hor is. How about that? Hor is reflection. R E F. All right. So again, little minute movements are not picked up. So all right, this is going to be in cursive. There we go. All right. So horizontal reflection. Um, horizontal reflection. That doesn't make sense at all. I mean, I guess it kind of does, but let's do it this way. Reflect about x-axis. That makes more sense, okay? So reflect about the x-axis. The third thing we're going to do, looks like it's going to be we're multiplying the parent function by a number greater than 1. So it's going to be a vertical stretch. Yeah. Okay, so vertical stretch. And then the last one we're going to do is we're going to go down 1 unit, okay? So I color coordinated all that because I'm going to put that on to the graph over here, okay? And in each case, at least my moving around there, I'm going to be I'm using this landmark here at 0, 0. I'm going to moving it left. I'm going to reflect the whole entire graph, and then I'm going to move it down. Okay. So first thing, here we go. We're going to go to the left 3 units. So, and again, it's kind of an imaginary thing here, right? 1, 2, 3. So we're going to go left 3 units. Like this. Okay. And then we're going to reflect it about the x-axis. So we're going to reflect it about the x-axis. We're going to go down like this. Okay. And there's next we're going to have a vertical stretch. So vertical stretch, we're just going to kind of pull it closer, tighter together, right? So we're going to go something like this. And I'm off the x-axis now, so let's actually do it like this. And then we're going to go down 1 unit. And again, I'm going to take this landmark here at negative 3, 1. Wait. Yeah, negative 3, 1. We're going to go down 1 unit. So, 1 unit about right here. So it's going to look something like this. Okay. So again, that was all the transformations. And it's not even close, is it? Oh well. I'll give you a good one. I'll give you a better one. How about that? And again, you can watch the animation. Click on it, look at the book, click on it, and you can see how we get that nice, pretty graph there. Okay, let's actually try to fix this a tad. I want it to look somewhat close to that 1, don't I? Is that? You notice how I kind of contrived that line. Oh well, here we go. There we go. All right, so that was all of our transformations. That's how we do transformations on functions. Okay. So okay. Last up is going to be piecewise functions. And again, piecewise functions. Please don't be like me. Please don't make it go in one ear and out the other. They are pretty simple. Again, once you realize it's not just one function, it's 2 or 3 or 4, however many you see inside of here. Okay, so this piecewise function. So in section 3.3, we learned that a piecewise function is a function that is defined by more than one rule. In example 8, a piecewise function is defined by 2 rules. Okay, so these 2 rules are right here. Okay, each rule requires the use of transformations to sketch the graph. So we're going to have a lot of fun here sketching this graph. So let's see if do they have a okay, good, they do. Nice, good job. Okay, but we still do our rough sketch first, right? Just to show the thought process, not necessarily perfection. Okay, so we're going to denote the top row in red and the bottom row in green. Okay, so the top row. All right. Well, what is the parent function of the top row? Well, it is an absolute value function. Golly, I don't think I've ever taken that off first try, have I? It is the absolute value function. Perfect, okay? All right, well, what transformations am I doing on the absolute value function? All right, well, it looks like what I'm doing, all right, first is going to be a horizontal, and I'm just going to put, to the left 2 units. All right, it's going to be horizontal shift to the left 2 units. And then the second thing I'm going to do is I'm going to reflect. Jeez, it is a lot harder to write on this than you think. Reflect. There's supposed to be an A there. About x axis. Okay, we're going to reflect about the x-axis, and that takes care of that. Okay, so let's go ahead and do that. So again, we have the absolute value function looks like this. We're going to shift it to the left 2 units. Okay, so shifting it to the left 2 units, about like right here, right? Like that. All right. And actually, I think well, let's actually we are gonna have to make tick marks. I'm sorry. We'd have to make tick marks mainly because we have defined domains here. So looks like we're gonna go. We'll just do the x-axis there. So again, let's try this again. So we're gonna go to the left 2 units, like this, and then we're gonna reflect it about the x-axis. So it's gonna look more like this. Okay, but remember that right here defines the domain of that piecewise function. So this piecewise function is this red graph down here, but only for the values that are strictly less than -1. Okay, so what I'm going to have to do is I'm going to have to, let's say, okay, it looks like this, but I'm going to have to tear it off right here at 1. Okay, so let's erase. So we're going to go down here, we're going to go down, and then we're going to make an open circle there. Okay, and that takes care of the first part of the piecewise function. All right, the second one, all right, the second part of the piecewise function is the square root of x plus 1. All right, so the first step I'm going to have to do, all right, I guess it's just 1, it looks like, right? It's going to be a horizontal shift. We're going to be shifting it to the left 1 unit. Okay, so let's go ahead and reimagine the absolute value function. Looks like this. Okay, and if I'm shifting to the left 1 unit, right, all I'm doing is shifting this to the left 1 unit, and it's going to look like this. Okay, and I guess that's actually it, right? So this is for all values that are greater than or equal to -1. Well, it just so happens we don't even exist below -1 anyways, right? So we can just put a nice closed circle here, right? And there we have it. We have our piecewise function with our transformations. And again, a nice pretty graph there. Okay, and I believe that, oh yeah, we'll do the summary. Holy smokes, that's a all right. So this is what all I said today, summed up, right? It's a lot of stuff. I'm not going to go over that. That's going to be on the notes for you. I'm pretty sure we hit the examples. Yeah, yeah. All right, so that concludes today's lecture.